Okay, students, welcome back. In our previous lecture, we learned about Copernicus and how his explanation of what's going on in the heavens can explain some of the most interesting observations, like the brightness of Venus and like the retrograde motion, for example. Today we will talk about the next stage, which is the era of precision, and how the era of precision brought about a big revolution into astrophysics, from astronomy to astrophysics. The transition to precision happened almost by chance. One of the most enigmatic characters in history of astronomy is Tycho Brahe, a Danish professor in our university by name of Inga Bolk, tells me that actually it should be pronounced Tycho Brahe. Doesn't matter. He was a nobleman whose twin brother died young, and he himself was kidnapped and raised by an uncle, and then went to the university, lost his nose in a duel. He believed in a hybrid model where the Earth was in the middle of everything, but everything revolved around the sun that revolved around the Earth. And he, being a nobleman and all, got a huge gift from the King of Denmark, which wasn't Hamlet's father. And the King of Denmark gave him an observatory in the island of Hven, or Hven, in the middle of the Baltic Sea. In it, he constructed huge protractors that you will see on the slide that pointed in different directions, thus, like you do in your observation in the lab that you have to do. You're going outside and you're measuring distances in terms of angles by fingers at arm's length or fists at arm's length. He used those huge protractors for the same exact purpose. Okay? For 40 years he collected observations of comets, novas, that's near stars, and of course regular stars and planets, the moon and the planets, comets, novas. At age 60, he was kicked out of Hven. The reason was that there was a new king of Denmark that didn't like him. So, Tycho Brahe moved to Prague in present-day Czech Republic. And he hired an assistant named Kepler. Kepler had his own crazy model of the heavens before he got Tycho's data. His model, described in the bottom right of the slide, assumes that each of the heavenly spheres now going around the sun is supported by one of the Platonic solids. Both models were proven to be completely nonsense. What Kepler did find was Tycho's detailed observation in the island of Hven, and those were observations of, for example, Venus and Mercury as morning star and evening stars, and they didn't exactly agree with a circular motion around the sun. Neither did the other planets such as Mars, Jupiter, and Saturn, only that time around it was the retrograde motion that was a bit bizarre. After many years of looking at the data, Kepler came with an alternative model to his own. He had to completely abandon his old model for planets that move in orbits that resemble ellipses. Is the sun in the middle of the ellipse? What do you think? Kepler's answer is absolutely not. The Sun is in one of the focal points of an ellipse. What's in the other focal point, you may ask? The answer is absolutely nothing. The Sun is in one focal point, and there is absolutely nothing in the other focal point. What Kepler did find from Tycho's detailed observations was the fact that Venus and Mercury, as morning stars and evening stars, don't act as if they move in a circle around the Sun, as we've seen in the last lecture. Not exactly. Neither do the outer planets, Mars, Jupiter, and Saturn. They didn't know of any others at the time. Planets move in orbits that resemble ellipses, with the Sun not in the middle, in one of the focal points. As you can see in the picture here of how to draw an ellipse, you use a string and two thumbtacks and you draw an ellipse, whereas a string and one thumbtack gives a circle. The Sun is in one of the thumbtack positions, and what's on the other side? What's in the other focal point? Think about it for a second. The answer is absolutely nothing. Ends up that the planets just get faster and faster as they get closer to the Sun, and so they kind of ricochet or slingshot from the place where they are at the closest to the one focal point, and then they slow down as they move away from that focal point, and then again ricochet or slingshot when they get closer again. So the speed changes, but the Sun is in one of the focal points and there's nothing in the other. The first picture here is the picture of the orbit of Mercury around the Sun, with the ellipse this time around standing on its hind legs, meaning kind of stretched upwards, the focal point being in the upper part. Now look at it and see that Mercury itself is moving in an orbit that's shaped like an ellipse. This has been actually done by students. All you need is to look at the maximum elongation and minimum elongation of Mercury each time it's close to the Sun. Basically, sometimes Mercury, like Venus, is an evening star, sometimes a morning star, and sometimes it rises like 2 hours before the Sun, and sometimes it's set at most 1 hour before rises at most 1 hour before the Sun does, when it's a morning star. These differences between the maximum distance from the Sun at sunrise and sunset for Venus never change, because Venus moves on an almost perfect circle. But for Mercury it does, because Mercury definitely moves on a very elliptical orbit. One more thing that Kepler found was that when a planet is closest to the Sun, it moves the fastest. This agreed with his observations perfectly. His law states his second law, the first being that the planets move in an elliptical orbit with the Sun in one focal point. The second is that the radius vector, and that's the line between the planet and the Sun, sweeps equal area at equal times. It's the same as saying that it moves really fast when it's close to the Sun and a bit slower when it's away from the Sun. Believe it or not, this is the first scientific law of the scientific age, except for the inertia that Avicenna found. I'll give you a few more seconds this time around in trying to answer this question here. You remember that the retrograde motion is when planets seem to basically skip a little bit towards the east every night until they reach retrograde, which is exactly when they're opposite the location of the sun, meaning you see them at midnight. And that retrograde motion is this drift to the east, then drift to the west, then drift to the east again. This is all for retrograde motion within the same plane as Earth's orbit around the sun plane, called the ecliptic. If it is a little bit outside of the plane, then you get like little circles or a Z shape for that motion east and west. But how would it change if the motion was elliptical motion? That's a very challenging question. So I'll give you extra 1 minute almost. As you are drawing this from above and from your perspective, I'm just going to be whistling a tune. Ready? Go ahead and answer this one. Now let's try and see again what the difference was between solar days and sidereal days. Basically, if you look at the sidereal day, let's say you're looking at a constellation called Gemini. So Gemini rises in the east, sets in the west, and crosses our meridian, the imaginary line from north to south, at certain time of the night. Let's assume it crosses at about midnight. Now the following day, it will actually cross a tad earlier than that. Sidereal day is 23 hours and 56 minutes, whereas solar day, which is the time from meridian crossing to meridian crossing of the sun at noon, that's 24 hours. But that's not exactly 24 hours, because as we're very close to the sun, which happens on January 4th, we're moving a tad faster. As a result, which one is longer? The solar day, that is when you're very close to the sun, or the solar day that's usual? Again, long time, so this is a little tricky. Again, I'll sing something. And the cat just said it's time to stop. So since Earth spins around its axis once in 23 hours and 56 minutes, that's still going to be the sidereal day, 23 hours and 56 minutes. But the solar day, when we're closest to the sun, notice that's on January 4th. That is summertime in Australia and winter time for us. Okay, when we're closest to the sun on January 4th, Earth moves in one day, not the usual 1 degree, right? 365 days, roughly divided that for 360 degrees in a circle, so it's roughly a degree, but not on the shortest, not on the closest to the sun. When it's closest to the sun, it's a tad longer angle because we move faster in this system. As a result, if the sun is above your head at the start position in this slide, and would be above your head at the circular orbit position A. It's not yet above your head in circular in the position B, which is where you'll be on an elliptical orbit after 24 hours. Therefore, solar day, the time from sun crossing to sun crossing on January 4th, would not be 24 hours, but a tad longer.